reaction centers. So if you are seeing, it is a monomeric unit which is having the globin part consists of 153 amino acids. It is also having the myoglobin also having two parts. One is the globin, as one another one is the heme. Heme is the prosthetic group, as we have seen in the case of hemoglobin. Here also myoglobin also heme is the active site. So the heme and the protein interaction is not covalent interaction. It is slightly what we have seen in the case of our hemoglobin. Likewise, here also the interaction is not covalent interaction. It is a simple the wrapping of the active site part. That thing we have to keep in our mind. This is the histidine imidazole, which is occupying the imidazole nitrogen will be occupying the fifth coordination position in the hemoglobin and myoglobin also. So it is from the starting itself, we are getting something different from that of the hemoglobin. First is the function. The function is differing. It is a oxygen storing protein. It's not a transporting enzyme. The another one is it is a monomer. But in the case of the hemoglobin is a tetramer. And remaining things, if you are seeing, it is iron 2 is present, which is present in the high spin state. It is the active site is nothing but our heme. Then heme is surrounded by the globin part. So again, it will protect the heme, iron oxidation and everything, whatever is seen in the case of hemoglobin. But what are the major differences between the hemoglobin and myoglobin that we are going to discuss? So if you are seeing from the structural aspect itself, it's hemoglobin is a tetramer, whereas myoglobin is a monomer. And it is a function, if you are seeing, one is oxygen transporting enzyme, whereas myoglobin is a oxygen storing enzyme. It is present in RBC, in red blood cells, hemoglobin is present, whereas the myoglobin is present in the tissues. In the O2 binding, if you are considering the O2 binding of the one heme unit in hemoglobin is supported by the other heme units. So it is a cooperative effect is observed. If you are seeing, the Hill constant value is 2.8. What is the Hill coefficient and everything that we will see in later slides. But the O2 binding is cooperative. Whereas in the case of myoglobin, O2 binding is non-cooperative. And dioxin binding to hemoglobin is a pH dependent. That is nothing but Bohr effect. So the O2 molecule, which is going to bind with the hemoglobin, that is influenced by the pH of the environment also. Whereas myoglobin, irrespective of the pH, it is having strong affinity for the O2 molecule. So in hemoglobin, the saturation of all the heme units with oxygen, molecular oxygen, will take place only at high partial pressure of oxygen. Whereas the myoglobin, even in the low oxygen pressure, myoglobin will immediately saturated with molecular oxygen. This is a plot which clearly indicates that the binding mode of the oxygen saturation property of hemoglobin and myoglobin are entirely different up to a certain level. So if you are seeing in the right hand side, so you are seeing two different kind of the plots. We are plotting the partial pressure of oxygen versus saturation with O2. So how much the hemoglobin heme units are saturated with molecular oxygen and with respect to the partial pressure. If you are plotting against partial pressure, you will get two different curves. One is hyperbolic in nature. If you are seeing here, even at low partial pressure also, myoglobin can easily be saturated with molecular oxygen. There is a up to this level, even between 0 to 1 partial pressure, there is a complete conversion of the deoxymyoglobin into oxymyoglobin. Whereas in the case of hemoglobin, initially, upon keep on increasing the partial pressure of oxygen, there is a slow rise in the curve is observed. Then it is going up to certain level. Then after reaching some maxima, it is again exhibiting the saturation behavior. So if you are plotting the point, connecting all the points which are passing through the 0 to 5 partial pressure Pascal, see you will get a S-shaped curve. The S-shaped curve is otherwise known as a sigmoidal curve. So one is having the hyperbolic, another one is having the S-shaped curve. Entirely both are different. So this clearly indicates that up to certain stage, the hemoglobin oxygenation is hindered only at particular partial pressure of oxygen, only heme can easily be saturated with molecular oxygen in the case of hemoglobin. But whereas in the case of the myoglobin, there is no such kind of effect is observed. Why this behavior? Different behavior that can easily be explained. So already we have said the hemoglobin is a tetramer, whereas the myoglobin is a monomer. So hemoglobin, in the case of hemoglobin, the partial pressure, even at a high partial pressure, only heme will be saturated with molecular oxygen. So the fifth coordination, due to the tetrameric cluster structure, the sixth coordination position is blocked by the valine isopropyl group. So upon oxygen binding, this valine group will be slowly ejected from the blocking position. So automatically this will change the conformation and salt bridge breakage will take place, and the next heme unit will have the some of the relaxed form. Then the consecutive steps, there is a relaxation will increases. That is the reason why we are getting the two different saturation curves. Is there any doubt? Is there any doubt?
No, sir.
Yeah. In the left-hand side, if you are seeing the graph, even if in hemoglobin there is no cooperative effect, then what would be the nature of the curve? The curve should be in the blue color line. If there is no cooperativity, then it will also looks like a hyperbolic, but there is not a great slope. Here the slope value will be less. But in the case of the green color curve, for myoglobin, the hyperbolic curve, the slope value will be very, very maximum. But in the due to the sigmoidal nature, we can come to the conclusion that there is a presence of cooperative effect. That's it. So this is what we have discussed in the previous case, that is shown here. This is the way how they are arriving the Hill constant. Y is equal to O2 divided by Kd, rate of dissociation, plus O2 concentration. If you are putting this value, then you will get a Y value. Y is nothing but Y or N, that is the Hill constant value will be arrived. So like myoglobin, hemoglobin saturation decreases as partial pressure of the O2 decreases. So that is the same case. In the case, if you are decreasing the, from this point, if you are moving to the left hand side, there is a low partial pressure of oxygen side. There is a saturation of the heme unit in myoglobin, as well as hemoglobin also decreases. If you are seeing the saturation curve, the curve is also going down. There is a general statement. Unlike myoglobin, hemoglobin at the same partial pressure, say 10 partial pressure, much less saturated. Yeah, if you are taking any one of the partial pressure position from 20 to 10, and if you are calculating the slope, there is a slope value for these two curves are entirely different. Here only there is no saturation at 10 partial pressure, 10 tars, there is no saturation of the hemoglobin is observed, whereas in the case of myoglobin, even at the 10 tars partial pressure of oxygen, there is a complete saturation is observed. Unlike myoglobin, hemoglobin binding is not hyperglobin. Yeah, it is sigmoidal in nature. The sigmoidal nature suggests that there are two states. One state is the slow reaction step. Another state is the fast reaction taking place. So this is what we have discussed. This is the way how they are arriving the Hill constant. Hill constant is obtained by considering these two, this reaction equilibrium. That is the enzyme plus n number of substrate. Substrate is nothing but our oxygen. So that will combine together to form the enzyme substrate complex. Enzyme binding of one or more ligands. That's it. Here enzyme, S is ligand. Ligand is nothing but substrate, or sometimes we will call it as a ligand. And N is a small number. It is a number that is we will put in the subscript of the substrate. So the equilibrium constant can be derived by E. Enzyme substrate complex formation is directly proportional to the concentration of enzyme and substrate divided by the concentration of the enzyme and substrate, the combined form. So YS is not how much the substrate bound. That can easily be calculated by considering the above equation. And if you are these two relation, the expressions are simply the inverse of this one. Y is nothing but the inverse of K. But only one thing, we are putting the N value in the prefix. So N is nothing but is a number of the ligands, how much number is added. So the partial pressure of oxygen